Great to be back in person. I think this is my first in person, in addition to the class lectures I just gave in the winter quarter at Caltech. Great to see everyone in person. And I think I want this to be very interactive. This is what I've missed with the Zoom talks, like just seeing people getting this real-time feedback. And so feel free to interrupt me anytime. Great. As you'll see from the title, it's a broad topic, right? So we want to do robot learning, and how do we have generalizable, robust learning algorithms for this? In some sense, robotics is like almost a moonshot challenge for many of the learning algorithms, because we are going from passive learning to interactive learning. We have safety, stability, all these requirements. And so many of the deep learning methods are brittle and they fail, right? So they wouldn't hold up in these real world conditions. And the other aspect is sample efficiency. You need to adapt quickly in real world conditions. So how do we design better foundations for learning with the view of robotics applications? So today I'll give you some of those foundational tools and show you some applications to robotics, and many of them are ongoing, right? So I think I'll also talk about some advances in computer vision, like self-supervised learning, I think are hugely important for robotics, but we haven't taken it all the way there. So there's a lot of potential for these different areas to come together. So when I think about generalizable AI, right? So generalization can work in so many ways. We have the standard definition of training and test distributions being the same, and can it generalize, right? That's how we get the theory of generalization. But in real world, you would need to go much beyond what I call extrapolation, like into scenarios that you've never encountered before, and test distribution being significantly different from training. And so that's where, in our brain, we have the framework of system 1 and system 2. And the system 2 is the one that's kind of helping us extrapolate, think rationally, maybe have symbol grounding, and through that have causal thinking and extrapolate to new scenarios. And so how do we enable that in AI? So I see 3 facets as being important, right? So we need very robust representation learning. And we humans are great at this. As infants, we are doing self-supervised learning. We are, able to do this foreground, background separation very effectively. And with that object-centric representations, right, we can build the view of the world and move around that very effectively. And that comes also with interactions, right? If you've seen babies learn, they're always touching, they're moving their heads, understanding the occlusions. So interaction is a key, and that's why I love robotics, although I didn't grow up learning robotics in my grad school because of this interactive aspects. When we can have better data, we can go look for challenging scenarios with passive data sets that wouldn't be possible. And the last aspect, and perhaps the hardest one, is compositionality, and with that, being able to reason about unseen scenarios. You could also call that zero-shot generalization. So you've not, seen you haven't seen a unicorn, but you've seen a horse. Can you still reason that it's similar to a horse, but it's different, right, in terms of its horn? So those aspects require, right, what we think of as system 2, because you not just have a representation, you're able to compose and generate and reason about scenarios that were never present in training. So to begin with, the foundation that I want to provide is what I call physics ML models. Broadly, when we think about physical systems, what are some challenges we want to solve in terms of complex multi-scale behavior, right? And how we can then use it in applications like the climate sciences that Marco just said. But also, why is that useful for robotics? So these are aspects I'll address. And to me, like why we need to rethink the use of machine learning in these scenarios is because our physical world is continuous, right? So many times we discretize because it's convenient. Even when we think about state action spaces, we try to discretize, right? And traditionally it's done in a hand-engineered manner. And then from those abstractions, we try to do low-level, mid-level, and low-level control. But what if we could come up with machine learning surrogates that can simulate these real-world phenomena very effectively and do it at different conditions, right? Because then that becomes a great tool both for design, how to design the right control for different physical conditions. But ideally, ultimately, for real-time control as well, because if you can generate, for instance, how turbulence is going to evolve very fast, then you can handle the turbulent conditions very effectively. So in these, the lens we want to approach this is through partial differential equations, right? That's a broad class of phenomena that can be represented from materials, right? Like material properties like elasticity, and these you can define it through Newton's laws of motion, and you can turn that into PDEs, as well as fluid dynamics. In most of these cases, the equations themselves are quite simple, but the phenomena they represent is highly multiscale, possibly even chaotic. So how do we have machine learning methods that can simulate this in a faithful manner? And that's a challenge. So as one example, we are looking in the context of control ultimately you want to be able to fly drones in turbulent conditions, but as a starting step, we can think about testing airfoils in these turbulent wind conditions, right? And here there are, we have our Navier-Stokes. We can model fluid dynamics reasonably well with Navier-Stokes, right? But we would still need to figure out what are the Reynolds numbers and how that is evolving. But the challenge is these simulators tend to be very slow, so you cannot have that be real time. So how can we use now machine learning instead to replace the traditional simulators? And then there is also the challenge that you may not be observing the whole force field. I mean, in this example here, you have the airfoil. You usually have a few sensors placed along the boundary or somewhere. You don't have the full force field. So there is this problem that there are hidden states. This is partially observed control system, a dynamical system. So we also have the additional challenge that we need to estimate the state, and we could use these partial differential equations to do the state estimation. And so that's what is traditionally done. This is called a PDE observer method. So where we essentially do the PDE backstepping to do the state estimation. So meaning if you have a sensor at the boundary, right, and given that observation on the boundary, you try to propagate that through the partial differential equation stepping, and with that get an estimate of the full state. So this is a classical method, but the main problem is it's too slow and not real time, right? So because you have to do the state estimation fast enough, because you have to control once you have this state estimation and keep updating it, right, with new measurements. So this is one problem we wanted to, use. You can describe this PDE observer, the state estimation problem, as a partial differential equation, but it is slow to solve with standard numerical methods. And so one application where you can use machine learning, if we can emulate these partial differential equation solutions effectively. So let me now give you some aspects of why we need a new foundation in terms of machine learning for such systems. So the main aspect is, if you look at standard neural networks, they're very much dependent on the resolution of the input, right? So, you have an input image of a certain resolution. You can train it very well. It'll work well in that resolution. On the other hand, you change the resolution, right? You may get very different answers. But this is a huge problem for solving partial differential equations because they tend to be highly multi-scale. You need to go to very fine scale and capture the fine scales to be able to solve the system effectively. But if you want to use a standard PDE solver, right, it has a lot of flexibility. You can change the grid, right? In the airfoil, there are different grids available, especially near the sharp edges. You want more discretization because there you could even have discontinuities. So those aspects, right, of having the flexibility of having different kinds of grids and different resolutions. So you can do that with a standard PDE solver using numerical methods. So how do we try to do the same with also a machine learning method? So let's say you have a trained neural network, but it should be flexible enough to give you the right answer. Yeah, so we have now, that's our requirement, right? So with standard neural networks, we would have to retrain the network with every resolution and every different grid. But by doing so, it's also overfitting to only potentially that resolution and not capturing the underlying continuous phenomena very well. Instead, if we have an approach that is resolution and grid invariant, we can hopefully capture the underlying phenomena better. And that's why we call it the operator, because ultimately, what we think of solutions as partial differential equations are operators, right? Because you have an input function space and an output function space. The input function space could be the initial and boundary conditions, like you saw in the previous slide. And the output is the solution function space. So these are, continuous spaces, and we don't want to limit to one discretization. And so that's the requirement. Now the question is, how do we go about building one? Oh yeah, I forgot, this doesn't work. So the principle is quite simple and similar to how you would do it in a standard neural network, right? You would have some linear operation in a standard network that can be, if it's MLP, just a matrix multiplication of a fixed size, right? Or convolution is also a linear operation. And then nonlinearity like ReLU or other ones. So we want a similar expressivity, but now in function spaces. And so for that, what we want to have is a linear operator, right? So this one should be able to accept any discretization of initial and boundary conditions. So if we can learn a linear operator, in certain layers of the network, compose it with nonlinearity, then we can have a universal approximator for operators, right? So I haven't still told you how, but this is a natural one. Start with a linear operator, compose it with nonlinearities, and you get an expressive model. So one natural design for this linear operator is thinking about what is the solution structure for linear partial differential equations. So if you recall your PDE class, right, there is the Green's function and its convolution with the Green's function, right? So any linear partial differential equation can be described in that manner. Okay, forget that. And so, for instance, this is the famous heat diffusion equation. There, in fact, you analytically know the kernel or the Green's function, and you can integrate through that. So you would have done this in your PDE course. Right? But in general, for nonlinear PDEs, we wouldn't necessarily have this form, right? So, but we can now ask if I can have layers that can solve this integral operator, which is nothing but a continuous convolution. So instead of small convolutional filters that are working on a discrete grid, right, at one fixed resolution, we want to learn kernels that can essentially do the convolution in the continuous domain. And now the question is, how do we approximate this well? Because if we can design now layers that can do such integral operators effectively, then we can compose them with nonlinearity and get an expressive model. And so that's where we resort to Fourier transform, you could also use other bases, right? Fourier is one example of a basis change because you could now approximate this convolution as multiplication in the Fourier domain. So this is a standard approach. And especially this is useful for many scientific applications because this is global. So if you do small convolutional filters in your CNNs, they're very local, right? They're mostly used for edge detection locally. But if it's like fluid flow, you need global phenomena, and Fourier transform can capture global correlations well. So that's another benefit. And we also know like these fluid dynamics are well described in the frequency domain, right? We talk about how the energy decays with respect to different wave numbers. So it's a good inductive bias, but it also makes it convenient to learn the mixing weights in the frequency domain. So what we are doing is doing the Fourier transform, learning mixing weights in the Fourier domain, and this is like a regularization. We only keep some low frequency components when we are doing the inverse Fourier transform, but we are composing it with nonlinearity, so it still has expressivity, right? So you want to trade off like how much you want to regularize and how much expressivity you want to have. But with this, what we are able to do is we have a network that can work at different resolutions because you can do the Fourier representation at any resolution, right? So that's the benefit of this method, that it is flexible. Even if you learned in one resolution, you can generalize and evaluate a different resolution grid. Any questions here?
Yeah, so I'm a bit surprised you said that, for example, in fluids, you're interested actually in the global information. That's what you said. To me, I don't see it right away. I would say, especially in these kind of physics phenomena, you're always interested in local information. And so generally, I'm a bit surprised that like this Fourier structure, which always, you have a very, very large domain. There's like a lot of information of the whole domain in the Fourier transform, right? But you're only interested in some local shock, for example. It seems a bit tricky.
Right, but once you know where the shock is, it's local, right? But determining where the shocks will happen, for instance, is global. And shocks happen in certain Reynolds numbers. In others, it could be smooth. Yes, I mean, like at any point of time, it could be local. But if you want to do a long trajectory prediction, right, you want to propagate the information globally.
I see.
And if you did like convolutional networks, the receptive fields are too small. It doesn't capture it very well. And the other, of course, drawback is it's tied to that resolution and doesn't generalize very well to a different one. That's a good point. Anyone else? Yeah, so this is our model proposal where we're doing quite simple operations. These are also fast operations with Fourier transform. And so by doing frequency domain processing, we are able to for instance, train on lower resolution data, and then directly evaluate it on higher resolution data and do that pretty accurately. Of course, you want to have some minimum resolution, right? It can't be too coarse a resolution because if you're not capturing enough of the frequency structure, you wouldn't be able to do it. But as long as it's good enough resolution, you can also do zero-shot super resolution. And so that's a nice thing about the flexibility of these methods. Yes, so back to our PDE observer, in this project, what we asked was how we can use this FNO to emulate the PDE observer. And we have, the main idea is as a state estimation, it's a recurrent network, right? So, we can also do like a standard recurrent neural network, but the benefit here is this is done in a resolution invariant manner, so captures the turbulence much better than a standard RNN. So yeah, some preliminary results. I should say we haven't still put this together with a controller, but for state estimation, we see promising results. So this is the conventional observer, and then we have the FNO emulate this and get about 2,000 times speed up. So, now I think there are many steps to see how we can, put that with the controller and do that in the airfoil system that I just described. So even though we haven't run that, we did a simpler model that does use Fourier basis to do a model-based reinforcement learning scheme in that airfoil setup that I mentioned. And we've already seen promising results here to be able to stabilize it really well, right? So it has much even lower variance of stabilization. Both the mean and variance you see are the lowest, and do it with much fewer samples compared to standard methods, like model free RL, and also model based. If you do standard LSTM, that's too many parameters to learn. So that's, I think, is another benefit of these methods. By doing Fourier basis, you already have a good inductive bias. You don't need to learn that basis, right? So you can learn a few coefficients in that basis. Yeah, so these are, I think, some promising results, but I do see lots of avenues where we can do both continuous time control and state estimation in robotic systems. And these methods, I think, can be very helpful there. So there have been many other scenarios where we have used these FNO, not in the robotics context, but for different modeling, like being able to predict stress in materials, which ultimately for manipulation of deformable objects, this is useful, right? So there, I think, can be nice use cases there, but also, right, like ultrasound imaging, lithography modeling. So lots of scenarios where you could have a partial differential equation system, but it could also be just data, right? So you don't need to know the PDE system. And if you have both, you can also combine both of them, what we call a physics-informed neural operator. You can also do the hybrid modeling. And so that's a nice flexibility these methods have. There's also a nice connection with transformers where, here we coined it the foundation models, right? So there is a lot of excitement and indeed a lot of, computer vision. We, in addition to language, also computer vision, we see a lot of good challenging cases are handled well with transformers because of their, again, much more global correlations, right, compared to CNNs with much, very small receptive fields. And so there is a nice connection because you can think of transformers as special cases of neural operators because the attention mechanism, if you, take it from a fixed sized matrices to a continuous generalization, that is an integration with the kernel. So with this viewpoint, what you can think of is the spatial token mixing you do in transformers. You could solve it through the Fourier transform, right? So you can essentially make self-attention more efficient by learning the weights in the frequency domain. So that's what here you can see the FNO as learning the full weights, but we can also make it more parameter efficient, and we had some block diagonal and other assumptions that make it scalable to even much larger models. So we have the ability to capture the same kind of quality as the full self-attention, but be much more efficient in terms of flops. Because the full self-attention is quadratic in complexity. And now with the use of fast Fourier transform, we can do it in linear time and still capture this effectively. Yeah, so recently we scaled this up to create a weather model, a global weather model. So you can see here the ground truth and the forecast net hour model being overlaid and being able to accurately predict these atmospheric rivers, which are very important for rainfall prediction, which, as we know in California, is a critical aspect. So in addition, we can do all the extreme weather predictions, cyclones, hurricanes, and we can do it as well as the standard numerical models, the current weather models that are running for several days, but be tens of thousands of times faster than those models. So with this, we can now do a large number of ensembles, right? You can have because you have such fast inference time, you can create good ensembles and get good uncertainty estimates and do effective weather prediction. Yeah, so this is one we've been really excited about, the possibility to combine it with data assimilation, take that and ultimately be able to replace the numerical methods that are learned today. Any questions here? Yeah, so all these capabilities, we are building at NVIDIA into a framework called Modulus. So you have these models available with fast GPU acceleration, really good documentation, easy to use guides. So I encourage you to go check that out if you're doing any kind of numerical methods for scientific modeling. I think this toolbox could be really helpful for you. And it's now also in PyTorch in addition to TensorFlow. So I think it makes it very flexible to use in a number of applications. Yeah, so that was one aspect that I think, what machine learning can bring to robotics, the ability to capture both physics and data-driven methods together, and do that in this function space domain rather than in a discretization. So you're getting better generalization and the ability to also run it much faster than standard PDE solvers, which, especially for environments like turbulence, is not practical to do it in real time. So now another aspect of, again, coming up with good representations, right, is these operational space models. Again, a classical notion in control, right? So can we do a transformation of our action space for more natural manipulation? But can we, again, make that data-driven? Instead of a fixed operational space controller like it's done classically, how do we make that be adapting online? And hence, we, again, get best of both the worlds. We have good physics priors, but we also are data-driven and adaptive. And so you'll see a nice combination here. And so that's the collaboration we had in our team, as well as the Isaac gym, which is the simulation environment where we've run this. It is GPU accelerated, and you can do reinforcement learning at scale, which is very helpful. And Josiah, who's actually here from Stanford, who interned with us. Yeah, so I'm sure you all agree that robot manipulation is challenging, especially if you're doing tasks like pouring, right? Like as you're pouring, the mass is changing, so it's very dynamic. So having it to learn from scratch from reinforcement learning is nearly impossible. There is a lot of possibility to explore, and it doesn't get to learn very well. And demonstrations may not always be effective. I mean, sometimes it is, but also how to get demonstration data and bring that in is also a challenge. And so, the main idea, as I mentioned, is how do we design the controller, right? So we can learn the policy, but in what action space representation would that be easy to explore, easy to learn the policy, and ultimately easy to adapt to changing conditions. Yeah, so this operational space controller is a classical method. So the idea is these end-effector commands and the compliance gains, we are transforming them into joint torque space. So becomes quite natural in terms of exploration. You can do that more effectively in this space. And especially for contact-rich environments, or tasks, this can be effective because you're directly handling these torques. So this is useful, but what this also requires is the knowledge of these mass matrix and these compensation torques, right? So something very much tied to the task and the environment. So if anything is changing, for the fixed controller, this becomes inflexible and the performance degrades. And so our natural question is how we can make this adaptive, right? Be data-driven and online adapt to residual changes, like have like a residual error to track and update this based on that. But at the same time have like this operational space representation to enable good exploration and fast learning. Yeah, so we do that as 2 stages. So in the first stage, this task agnostic pre-training, the idea is, right, you're giving it a simple task or some kind of a nominal task, right? In this case, like kind of tracing like, a simple shape here. And then task-specific fine-tuning, how do you then have it adapt to a new task and also adapt these mass matrices and others online. Yeah, so that's the idea. Like in the first stage, right, it's, you learn both this operational space controller and the policy together. And so you're learning the dynamics, you're learning the RL policy through PPO standard methods. But the idea is now, we're learning it through these, right, mass matrices. But now, if you want to fine tune to a different, So this operational space controller is right using learned mass matrix and compensation torques. But now with fine-tuning, we will further adapt it, right? So there is now a way to track the residual errors, right? And then ask, can I now update my estimates of these mass matrix and compensation torques as we go along? So it's, right, I mean, if you're always trying to learn from scratch all these parameters, it's hard. So trying to divide it into 2 stages. In the pre-training stage, you have a nominal estimate of all these parameters, and you also have a nominal policy. And so with that, can you quickly adapt to changes, let's say, in the, right, like kind of the task, like the puck, we change the friction, we change the mass. So if you're changing this, can you quickly adapt online? Yeah, and so you can see that with the path tracing here, we first pre-train it to do the circle. You can ask zero shot without any retraining, how well does it do the tracing? So in this example, both even the OSC is reasonably able to do because the mass isn't changing much online, right? But we do see with zero shot, it's a bit more stable. But especially for having it to, have a task that is harder, we observe that our fine-tuning is much, much faster compared to a fixed OSC because there it's having, right, like the wrong parameters and hence not able to adapt as well. This is much more pronounced in the cup pouring task because, right, so you can see with a standard OSC doesn't even learn how to pour because, the mass matrix, you want it to be flexible and changing dynamically rather than a fixed one. And now if you try to pour twice the amount as in training, right, our model still somewhat does it zero shot, but with fine tuning, it is better. And so this aspect of, I think, adaptivity, but at the same time, having good pre-training to learn a good nominal model is a good one. And same with puck pushing as well. If we change the mass and the friction, we see it adapt much better. Yeah, so you have more details here, and it's as I said, done in Isaac Gym, and this is available online. So I think this is something that you can build up further as well. Yeah, so to me, the main takeaway is if you're trying to do reinforcement learning in these challenging cases, it needs a lot of data. And even if you do that as pre-training with extensive training, you would still need our online adaptation because we're constantly changing our tasks. We're changing environmental conditions. Here we still didn't do sim to real, but if you were to take it to the real world, there would always be some changes in specification, right? Like these kind of mass matrix, torques, you can never perfectly describe. The friction you can never perfectly describe. So I think these aspect of having enough flexibility to online adapt, but learn good nominal models is a good balance. Any questions here?
When you were kind of adding this representation of the mass and so on, did you use any, like as an engineer, did you use physics-informed approach to be like, we know the situation decomposes like this, or was it a black box kind of approach?
I mean, so it is physics informed in the sense we know how the OAC handles the mass matrix and those, right? So that's kind of from the operational space transform. But the learning the mass matrix and everything, we just kept it flexible. Because there, we don't want to impose it because we want the flexibility that it also adapts to changing conditions. Great. So I guess I have like another 15 minutes. Is that? Yeah. So that was one example of having good reinforcement learning principles and doing that in simulation. But if we have many others. These are legged robots. This is from almost a couple of years ago now, where we showed in simulation you can have this legged robot do all kinds of tasks and directly do sim to real by doing it as hierarchical reinforcement learning. And so I think having there's a lot of open problems here on how to design good curriculum in simulations, right? What is that right set and how to do good sim to real transfer. We've also been doing that in the realm of robotic surgery with collaboration with Andrew Hung, who is a robotic surgeon at USC. And their simulations are used to, in fact, train surgeons. So we can ask how we can assess skills in surgery. And also there are live surgery videos, right? How we can kind of correlate the skills across these different ones. So I think starting with like kind of good computer vision models to do gesture recognition and then be able to assess that, I think is a good first step. But ultimately, we can also ask about reinforcement learning, and with that, give real-time feedback to surgeons to say if there are some corrective measures based on the trajectory they are taking during surgery. So I think there are a lot of interesting and open problems in these areas. So I encourage you to check out Isaac Gym if you haven't done already, because I believe we can do these now reinforcement learning at scale. I think earlier the Oscar, we did that over thousands of agents, right? So this is not something otherwise would be possible. So having both the physics, everything done on GPU as well as reinforcement learning makes it very effective and easy to scale. Yeah, so in the last part, this is more computer vision, but I believe are really important for robotics. So I, want to present some of the latest advances we've made. Indeed, foundation models have been, really getting big, but also multimodal, right? So, and how do we make sure they're robust, they can do compositional understanding well, and what are the right self-supervised learning losses to enable them to do so. And this becomes very important because these are large models, but we also want them to have good representations for many tasks. And so now we are seeing self-supervised learning even beat supervised learning on many tasks, and that is very promising. And the visual reasoning is like kind of, as I mentioned in the beginning, the system 2 aspect of it, right? And how do we build that into these models? Do we need explicit symbol grounding, or can we do that implicitly? But what are, again, some good self-supervised learning losses to encourage better reasoning? So I think, that's a broad brush. But these are some concrete works that are advancing these questions. So for instance, the disco box that appeared last year at ICCV, what we are able to do is use only bounding box supervision. So the only annotations you need in training data are these bounding boxes. But you can directly get the instance segmentation and correspondences from that in a self-supervised manner. And so you can see here right, so with bounding box, it turns it into segmentation masks very accurately. So this is a random YouTube video, not from the training data set, and it's able to do it well. So I think these kind of methods can be very effective because getting segmentation annotation is so much more expensive than getting bounding boxes. And so it's a good intermediate step before going to fully, right, unsupervised learning. So as I mentioned, the other aspect is also designing good transformer models for tasks beyond just classification. So segmentation, our segformer model is lightweight, but also can do zero-shot robustness very well. So you can see here, this corruptions were not present during training, but it's still able to handle that pretty well and get good segmentation. And I should mention in both of these, they're not video-based models, right? They're just frame by frame, but still you see good consistency. So even without enforcing any. So that shows the promise, but obviously we can also add temporal consistency to further enhance these results. And so at NVIDIA, we are building the Disco box into the AV stack to remove the need for segmentation masks. So it's about a few thousand times faster than how humans can annotate, right? Because we do have human annotators. We can look at the time comparison and see that it's a huge reduction in those efforts. So this is an ongoing effort with the AV team, by Jose Alvarez, and so we're very excited about this. So as a next step, what we did, this is appearing in CVPR, is to also remove those requirements for bounding boxes. So this is based on the Solo backbone, if you know. But the main idea is we can iteratively refine coarse masks. So there's a coarse mask proposal you can get from the attention layers. But with self-supervised learning, we can refine them and we can make that into really good segmentation masks. So I think these are results that are promising, because if we can completely do away with supervision for intensive tasks like segmentation, I think that can be very helpful in a number of scenarios. So those are still vision problems. We haven't taken them to action and robotics, but this one takes it all the way, in the sense we want to do manipulation of these deformable objects. So this is in Omniverse, the NVIDIA platform for universal visualization. So what you see here is the ability to manipulate, if we say this is the start state, this is the target state we want this plush toy to be in, we can learn the model of how it is going to deform and learn to manipulate. And so I'm not giving the details here, but we are using implicit representations for correspondences, occupancy, the flow field. So a lot of the recent advances in implicit models, for geometric understanding, we can use that, and with that also get good ability to manipulate deformable objects, which is more challenging than rigid body. So I think those are some useful aspects on adding structure. The other is also creating good benchmarks. How do we have the ability to measure generalization, right? So in this Bongard HOI, which will appear in CVPR, what we are saying is let's create good benchmarks for systematic generalization. So here it's a few shot learning benchmark where, as you see, there is a set A, right? There's one set, another set. And we want to ask, does the query belong to set A or set B? So what do you think is different in these two sets? What is the underlying concept?
I guess set A seems to be a lot more people racing bikes.
Yeah.
Whereas set B just tends to be pictures of bikes in more general applications.
Exactly, right? So it's we are trying to give challenging binary classification problems using only few examples. Because it's very easy to cheat in a lot of these action recognition data sets, because if most of the time the person is riding the bike, right? Just the presence of a bike already signals the relationship with the bike. So what we want to do is disentangle just the object recognition from relational reasoning. And so with this data set, we are able to create these kind of careful hard negative examples where we still have the objects, but their relationship changes. And so this, we did it on the existing, I think it's called the Hague data set, but it required a lot of human curation because there were a lot of false, both positives and negatives. So it shows many of the benchmarks we have are quite noisy. And so it's important to think about these kind of challenging ways to test machine learning methods, because we are, it is not easy to cheat on this. And we do see that, we can ask human annotators, and they can very easily still figure out these relationships, But even state-of-the-art models have quite a big gap from what humans can do. So this is more as a challenge than a solution. If you can solve, if you have good few shot and these capabilities, I encourage you to try out this data set. And I think, there is the aspect of how we can do the relational modeling better. So related to this relational modeling, what we call a relational, reasoning with vision transformer or RelVit, this will appear in iClear. I think, it's important to think about good self-supervised learning methods that encourage this relational reasoning. And so this is something we built explicitly into, frameworks like Dino, that's an existing backbone. But the main principle here is to, think of learning a dictionary of what are the features corresponding to different concepts, And so that way, the concept of riding a horse, can we dynamically change that feature set and be able to better learn a model for reasoning. So we are getting promising results on benchmarks, but I would say this is still a work very much in progress in terms of how to do good relational reasoning. But I think the power of self-supervised learning with good benchmarks and thinking of both local and global ways to enforce self-supervised learning and consistency for relational reasoning can be very effective. So that was I gave kind of a few snippets. I'm sorry if that was very fast. I didn't dive into those methods, but I do think some of these latest advances in vision with self-supervised learning, these robust foundational models, more reasoning-based models, could be very useful for robotics. So I look forward to seeing lots of works bringing these together. So as a conclusion, I think, I hopefully convinced you there's a lot of exciting foundational aspects of machine learning that are very relevant to robotics. And the ability to capture scientific phenomena like fluid flow that is multi-scale, potentially chaotic, using good machine learning emulators that can transfer across resolutions that are much faster than what traditional methods can do is very promising. And in the same realm, using our, all the knowledge from control theory, I feel like we should very much focus on how to exploit that well, but do, little of learning, how do you kind of think about residuals or add learning in a lightweight manner to adapt it quickly, I think can pay off a lot. And, we really need this intersection, a lot of reinforcement learning on games has been from scratch or without much inductive bias, whereas in robotics, that wouldn't fly. We have to very much start I believe, from a controls perspective, but kind of debate where learning should be added, how flexible should the models be, and as much as possible, bake in and the physics and the inductive bias as possible. And I do think the simulations are crucial to exploring this at scale because we can change environments, we can change tasks much more easily. And sim-to-real, I would say, is still very much open, especially if you want in the real world, in the wild, for it to adapt very quickly once we train it in simulation. And lastly, this aspect of compositional AI, foundation models, I think, are the future. At least that's the only one we have so far. And that power of large-scale pre-training, with web-scale data is very promising. But it remains an open question of how do we turn that into robust, compositional reasoning. How do we have zero-shot robustness to different kinds of corruptions and have stability and safety guarantees? I think all these are still open, but I do think there's a lot to be explored there. Thank you.
Any questions? We have a few minutes.
Yeah, so I guess just for an example, let's say working on, I guess just for example, let's say you're working on something like proprioceptive motors for better locomotion, and let's say I want to use like sim-to-real. So given the current state of like the field of sim-to-real, like what are examples like some more like open problems and like, that like if they are solved would make like the field a lot better?
Yeah, so a lot of the sim-to-real tends to work as hierarchical reinforcement learning, right? So you spend a lot of time debating what is the level of abstraction you want. So in the legged robotics case that I showed, we were like saying there's a dictionary of movements. There's walk, there's like kind of, I guess, step, there is trot, and they do that at different speeds. So there is like, you need a basis essentially of primitive actions. And so that we all need, like also in the real world, the robot to be able to do that well, right? So under that assumption, what the reinforcement learning is doing is learning how to compose these primitive actions. But in so many examples, that is also hard to come by. For instance, on Cassie, the bipedal robot, which we are now exploring it in simulation, getting like, right, nominal controllers is hard enough. Like if you ask it to, walk, even that under different friction is hard. I mean, right, you can never, no one knows how to make it jump. So, there's still a lot of hand engineering needed, and that's a good start when we can do it. But in many cases, we don't know how to come up with those right primitive actions and the right controllers for that. And sometimes it may not even be the right level of abstraction, right, depending on the task. So I would say that's an important open problem.
I do have a question. So when you were saying that with the Fourier neural operator method, you were obtaining 1000x speedups with respect to full-blown PDA solvers. Were you comparing with respect to full-blown PDA solvers?
Yes.
Or with respect to reduced order model type of approaches?
Oh, yes. So these are, a lot of those are like pseudo-spectral solvers. So in that sense, they're, right, they're considered like the efficient implementation for that setting.
Have you also considered, there is a community that leverages basically projection-based methods to dramatically reduce the dimensionality of the problem to something that can be actually solved quite quickly. Right. So I was wondering whether you also made a comparison to those methods, like ECSW in the case of in a nonlinear setting and so on.
Yeah, that's a good point. So in a way, these pseudo-spectral solvers are like kind of doing reduction in the Fourier domain, right? So that's one class. So we mostly like kind of write our collaborators in that domain, like what they think are the current practice for different domains. For instance, for the PDE observer, there's like prescribed time. There's different kinds of state estimation within that. So we basically like kind of use their guidance in terms of what they consider as state of the art.
And assuming that the solution provided by the full-blown PDE solvers can be considered the ground truth, what did you see as accuracy gaps?
So not much. These were like kind of either 10 to the -2, 10 to the -3 kind of realm. So it depends on the application, right? And that's also the other aspect. In so many of the applications, there are modeling errors that are much bigger than these. So we may not, whereas the standard approach has been to go to very low errors with standard solvers. And there you have to do that because unless you do fine scale discretization, you will get very wrong answers, right? It doesn't converge. Whereas with, I think, the machine learning methods, you can get away with higher errors because anyway, these are assumed models in real world applications. In fact, with the weather setting, we assume no physics right now, right? It's completely data driven. And it's able to, in fact, many times beat the NOAA, the standard forecast estimates for hurricanes and other models. So I think that shows that maybe, right, sometimes if you have enough data, like in the case of the weather, we do, maybe dropping some of the modeling assumptions and seeing what a purely data-driven method can do is a good start.
Does it outperform the NOAA model across all the scales, or there are regimes like, in the short horizon where one model is better than the other one?
So I would say, like, these are like working similar to those models in terms of, like, say, there's ACC, there are like extreme right events, percentiles, we can compare those up to like about 4 to 5 days for precipitation and other variables that's considered very challenging. So after that, we are seeing a deviation, and I do think there we need to impose more physics, right? Because for the longer term, you have more chaotic behavior, so we need that, and that's something we plan to pursue further.
All right, I think we have time for one more question, if any. If not, let's thank again the speaker. Thank you very much.
Thank you.